optimization. In this section, we're going to talk about how to find the maximum or minimum value of a function. When we do that, it's called finding the optimal solution, also known as optimization. So the whole idea of optimization is to find the max or min. That's the whole idea. Find the max or find the min. And we already know how to find the max min. There's actually lots of ways to find the maximum of a function. One way is to just graph on your calculator, and we will talk about that. We'll do an example. So again, if you get to use a calculator, if this is paper 2, you just literally just graph it and find the max. Right? You have a little graph, find where the max is. Another way, if you know it's a parabola, then you can use the vertex formula. Right? Go to algebra 2, go old school. And the last way is the way we're going to talk about today is using calculus. And I got news for you, we already know how to do that. Right? The way you find the maximum of anything is you take the derivative, set equal to 0. Right? Plug in your test point to see where the maximum is, or undefined, by the way. But that's what this lesson's about. It's all about how to find the maximum of different things. Let's move on to the thing we got to watch out for. So let's look at this example right here. Let's find the x value of the maximum from 2 to 6. So again, notice this is from 2 to 6. So on my little graph right here, I'm only going from 2 to 6. Well, the max would be right here. Right, so at 3. So then let's look at this example. What's the maximum value? Find the x value of the max from 1 to 7, right? So now we're going from 1 to 7. Right, now this is still relative max, but it's not the max. The max is actually right here now, points higher. So it'd be 7 would be the x value would be 7. And that's the thing we have to watch out for. When we set the derivative equal to 0, we find the relative maximum, and that a lot of times that is the max, sometimes it's not. It's all about what our interval is. So that means when we're looking for the max, the way we find it, to find the max or min, is actually, first we set the derivative equal to 0, right, to find our critical points, or undefined, to find our critical points. And then when we hit those critical points, we're gonna plug them into original function to find the value. But we're also gonna plug in the endpoints. Right, so the endpoints could also be a max or min, like this graph here, right? So if you set the derivative equal to 0 and find critical points, you're gonna get this point right there, you're gonna get the point right there. But if I'm looking for the max is this thing right here. So how would I find that? You gotta worry about the endpoints also. So general idea is, right, when you want to find the max or min, take the derivative set equal to 0, find your critical points like we've always been doing since the beginning. And then this time we also got to check our endpoints. So that's a big new thing. Check your endpoints. So let's talk about how to find the max or min. There's actually lots of different ways, right? So when we want to test optimal solutions, so we want to check something's actual local max or min. There's lots of ways. We can do the first derivative test, right, where we do our sign diagram. That way it works. And we find set the derivative equal to 0. And then we can do little sign diagrams. Right? Plus minus is the max, minus plus is the min. That's one way to make sure something's an actual max. The way Ivy loves you to check your actual max when we're doing an optimization problem is a second derivative test. This is what we talked about earlier. Ivy loves this for maximum problems. That is a terrible heart. That one's slightly better. I'm gonna let that one go. Right? But Ivy loves to tell you to find the max and then check using the second derivative test. And actually, it's a lot faster if you do it that way. And the whole idea of second derivative test is you find your critical points, and then you plug them into the second derivative. If you get a negative, it's a local max. If you get a positive, it's a local min. So you find your critical points by saying the first derivative equal to 0. Then you plug those critical points into the second derivative. Another way to do it, especially if you have a graphing calculator, right? Especially on paper 2, you just graph the thing, right? So if this is paper 2, and they give you, and it's like, what's the max of this? A lot of times what happens is you have to take the derivative, and then I was like, hey, what's the max of this function here? And all you can do is since you have a calculator on paper 2, you just put in your calculator and graph it. Find the max, and you're done. Right? So the 3 was to test the thing's the max, right? So most of the time you're going to find the critical points. So that's the derivative equal to 0, find your critical points. How do you test if it's a max or a min? Well, you do the first derivative test, like make a sign chart, or you do a second derivative test. And again, if you get to use a calculator, you just graph it and do it that way. Okay, let's talk about how to actually do an optimization problem, right? So these are basically word problems. To find an optimal solution, we need to follow these 4 general steps. write an equation where you're trying to optimize. So generally there's going to be an optimization. There's an optimization equation. So this is what you're trying to optimize. A lot of times it's like, oh, area is like length times width. And then if you only have one equation, then you just take the derivative that equals 0, blah, blah, blah. If you have two variables though, like the width, generally be a second equation. And use that second equation generally is a constraint equation. They'll tell you, oh, the perimeter is only 100 feet. Or when you add these things, it equals, I'm not sure what that spells. It equals, when you add these things, it equals 8 or something. So if the equation from number 1 has more than one variable, find the equation of constraint, or in other words, find an additional equation. Right, so that's the way it's generally going to run. They'll give you an optimization equation, like find the max of this, or find the min of this. And then they'll also give something else, like, oh, you only have 20 yards of fencing, and that's going to be your constraint equation. And then use a constraint to algebra. So then you're going to solve the constraint for a variable, plug into this variable, and solve. That's kind of the idea. So it will make more sense in context, but the general idea is writing the optimization equation. If you need a second equation, they're going to give you some information for constraint equation. The whole idea is you have two variables. You want the same variable, so you're going to solve one, plug it into here. And once you do that, then it's basic calculus. Take the derivative, set equal to 0, blah, 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 blah. So here's our first example. A farmer has 800 meters of fence and wants to create the largest rectangular enclosed area possible. The farmer is also going to use the edge of a river as one side of an enclosed area, so you don't have to worry about fencing that side off. This way the farmer only needs to use fence on 3 sides of the enclosed area. What is the maximum area the farmer can enclose? Right, so step 1, right, what are we trying to maximize here? In this case, it's the area, right? They said right here, what is the maximum area? So we're going to go. Now, a lot of times they don't give you the variables, you just make your own up. X and Y is fine. You're trying to maximize area, so how do you find the area? It's length times width, or in this case, X times Y. That's my optimization question. That's what I'm trying to optimize. Area equals X times Y. Now again, my whole goal is to take the derivative set equal to 0, but right now, I have nothing I can really use with this. We also know, right, so since it's two variables, we're going to try to find a constraint equation. What they told us, the farmer only has 800 meters of fencing. So that means all this only equals to 800. That's your constraint. That's right. So you can use constrained by 800 meters of fencing. So think about how you do fencing. It's perimeter. So the perimeter here would be y plus x plus y, also known as 2y plus x. Right, so this is my constraint. So again, we're trying to optimize this, and it has two variables, so I need another equation. Luckily, they gave us a constraint, so they gave us this. And all we need now is algebra. I don't want two variables here, I want one, so solve for a variable here. Easiest way to do is solve for x. In this case, sometimes it might be y. It doesn't really matter which one you solve for. So in this case, what do you solve for x is subtract the 2y. So you get 800 minus 2y is x. And we can plug it back into there. So my area is now going to be, instead of x, it's 800 minus 2y times y. If we simplify that, get 800y minus 2y squared. So that's my area. 800y minus 2y squared. Right, and that's what I'm trying to maximize. I'm trying to find the max of this. Or it works if you want to try to find the max or min, it's the same idea. Try to find the max of this. So how do we do it? Take the derivative, set equal to 0. So let's take the derivative. A prime is 800 minus, take the derivative, 4y. Set equal to 0, because that's how you find critical points. I get 4y equals 800. Divide by 4. I get y equals 200. Right? So y equals 200. Now, here's the thing. You can't just go like, I'm done. You gotta make sure that's the maximum. You gotta show it's the maximum. A lot of times they're gonna ask you, prove it's the max. So how do you know 200 is the max? Well, right, you have different ways. You can do a sign chart. But you see right here, if I'm doing a sign chart, I gotta plug in like 100 into that, or 0. I guess I can still plug in 0. And then on this side, you gotta plug in something bigger than 200 though, like 300 into that, and I don't wanna deal with that. So the easiest thing to do here is do a second derivative. Second derivative test. Right, here's my first derivative. If I take a derivative again, that goes away, I just get negative 4. Right, that's a negative, which means it's a max. So this is a max, you proved it's a max. Now what are we trying to find here? What is the maximum area? So I gotta find the max area. All I found so far is one of the sides. One side's 200. Right? So do we always do mathematics? Find the other variable. So we have y, go back, plug it in to find your x. X equals 400. So I have my two dimensions, right? So 400 by 200 fencing here. And again, the question is find the max area. Sometimes it might just be find the value of the long side or whatever. This question actually wants you to find the area. So my answer is going to be the area, which is 200 times 400, also known as 80000 meters squared, because the area. And that's the general idea of how we do optimization. We're going to do a few more examples, but the general idea is they're going to give you an equation, and the whole idea, if you want to find the max or min of it, just take the derivative set equal to 0. It gets a little more complicated when your equation has two variables, so that means I got to find another equation. If they do that, they'll give you another equation with a constraint. That just means it has that you could solve for one variable, right? So you have okay, I only have 800 meters fencing. I could set up the equation for that, solve for one of the variables, because you want to make this one only one variable, plug it in, so now it's all one variable. Now I can take a derivative set equal to 0. So took a derivative set equal to 0, solved it. I got my y equals 200. They're gonna want you to prove that it's max, right? You gotta make sure it's a max. So plug it in, either do second derivative or do a sign chart. In this case, second derivative is a lot easier. So when I took the second derivative, I got a negative value. Negatives are always maxes, so that tells you that is a max. Right, and now once I got my y, I plugged it back in to find my x, because the question was find the area. Sometimes just find the y and you're good. And I found the area. So that's it. Let's do another one though. A little more basic. Determine the max product of two positive numbers whose sum is 8. So this is actually the exact same type of problem. It just looks different because it's like a number problem. Look what the question is. Find the max product. So first let's put two numbers out there. Let's go x and y again, right? Those are my two numbers. The max product would be, well, my max is going to equal x times y. I guess the product would be, it is your life. Put whatever you want for your variables. I'm just living in it. So product is x times y. Right? So again, notice I want to take the derivative set equal to 0. I can't do it right now though, because there's two variables. I want to deal with that. So they tell you this other information. Two positive numbers whose sum is 8. That's your constraint. Right? So this is what I'm trying to optimize. My constraint is that when I add them up, sum, it equals 8. Right? So it's the exact same type of problem we just did earlier, just a much smaller scale. So I'm like, okay, get one of these variables by itself, it doesn't matter which one. Let's put x equals 8 minus y. Plug that into this one. There's no more x. 8 minus y times y. Right? Simplify it. 8y minus y squared. Right, and then again, I'm trying to optimize it, right? If you want to find the maximum of anything, take the derivative set equal to 0. So let's take the derivative set equal to 0. 8 minus 2y. I can solve that very easily. And y equals 4. Again, you're supposed to show that that's the max. How do you know it's the max? The easiest way to do is take the second derivative. So it's p prime. So p double prime. We derivative of this thing, which that goes away, so let's get negative 2 again. So again, anytime you get a negative, it's automatically a max. I don't have to plug anything in, because there's no variable to plug into. So it is a max. I checked it off. I got y equals 4. You generally want to find the x in this case, because the question is, again, find the max product. So plug it in. X equals 4. So my max product is going to be x times x, 4 times 4. Same idea, just wrong numbers. 16. That's the max product. But again, notice the exact same type of problem, right? They gave me some information. So here's my thing I'm trying to maximize. It had two variables, so I needed another equation. They gave me some other information. Hey, when you add these two things up, it's 8. So that's my constraint. try to get one variable by itself, plug it into the other one. Then it's always the same thing. You want to find maximum of something, take the derivative, set equal to 0. Make sure the value you get, because sometimes you get two values, these have been easy ones. Sometimes you get two values, make sure the value you get is the one you want to max. And then, right, by second derivative, that's the easy way to check that, and then plug it back in. This one that's a little different now. A psychologist claims the ability to memorize simple facts during infancy years can be calculated by the formula A of t equals t natural log of t plus 1, where t is between 0 and 5, so kids are between 0 and 5 years old, being the age of child years. So what's different about this one? It has limits, has endpoints. So we're going to check the endpoints, and I'll tell you what that means in a second. But the whole idea is we're going to check the endpoints, because it has them. The last ones we could have figured out what the endpoints were. Like over here, it couldn't be anything bigger than two positive numbers, so our domain was from 0 to 8, stuff like that. But here, they're very spelled out for you. You have endpoints. Also notice it's only one equation. All it gave me was that, right? So what's it? At what age is the child's memorization ability at a minimum? Again, we're trying to find the max or min. That's optimizing. We're trying to optimize this. And they only gave us this one equation. So how do you optimize it? Same thing we always do. Take the derivative set equal to 0, right? I don't need a constraint. I just have the optimization question. I have everything I need. So take the derivative set equal to 0. Now look at this derivative. That's a product rule, right? T times natural log of t. So take the derivative of the first one, 1, times the second one left alone, plus the derivative of the second one, 1 over t, times the first one left alone. And then the derivative at 0. So that's my derivative, set equal to 0. Natural log of t plus these cancel out, I get 1. So now we solve this, subtract 1 from both sides. Right, the way you get rid of t, the way you get rid of natural log is you take the e to both sides. So I get e to negative 1 equals t. Now I want to make sure that is a min. Now, right, this time we're looking for a minimum. So the best way to check it is use the second derivative test. Now, my second derivative of that, I gotta take the derivative of that again. So natural log, now a little easier now because I don't have to do product rule. Natural log of t, here's my second derivative. I get 1 over t. That's the second derivative, sorry. Plug in, now in this case I have a variable, so you gotta plug it in, right? Second derivative test, you plug in your critical point. So 1 over e to the negative 1, which is same as just e. That is a positive, so it is a min. So right now that looks like it's the lowest, my minimum, right? But I can't figure out my endpoints. Now, actually, don't have to worry about 0 because it has no equal to sign, so 0 is not a possibility, but 5 is. So how do we check which one's actually lower? We just plug it in. Let's plug in a of e to the negative 1, and let's plug in a of 5. Right? Because again, I have two possibilities. I have this one and I have this one. I want to figure out which one's the minimum. So I just plug back into the original value. Whatever has the lowest value is the winner, is the minimum. So if I plug in e to the negative 1, I get e to the negative 1, natural log e to the negative 1, plus 1. Natural log e cancel out, I get e to the negative 1 times negative 1 plus 1, which is this. E to the negative 1 is 1 over e, and that's a negative, so minus 1 over e plus 1. That's like 0.7 something. So that's that one. Over here, 5, natural log of 5 plus 1. Natural log of 5 times 5 is something like 3 point something plus 1. So this one's already bigger. So that one actually is my minimum. So at what age is the child's memorizing ability at the minimum? At age 1 over e. Good old math answer for you. 1 over e to the age. Which is it's like 0.382. I checked this a second ago. But again, notice how same concept on all these, right? You want to find the max, take the derivative set equal to 0. You want to find the min, whatever you want to do. Take the derivative set equal to 0. Only problem with this one was once I got my answer, I also had endpoints to deal with. Those might be the min, right? This graph might have been like this. I'm like, oh, that's actually the min, not the local minimum we found. So anytime you see endpoints, you gotta watch out. You gotta see which one wins. Does your critical point lower or is the endpoint lower? I didn't have to do 0 because I had no equal to sign, so it's not part of the domain. Okay, let's do another one. This one's a little more difficult. A rectangular cake dish is made up by cutting out squares from the corners of a 25 centimeter by 40 centimeter rectangle of a tin plate, and then folding the metal up forward to get this. So we're going to fold this up to get that. What size squares must be cut out to produce the cake dish of the maximum volume? So it's a little more difficult. Now look at the question. What size squares must be cut out? That's what we're looking for. So we're trying to figure out how much to cut out here. So again, I don't know what that is. I know this whole line here, all this looks like it's 40. And all this looks like it's 25. Now, I'm trying to figure out how much I should cut out. So let's make this x. That makes that x. That makes this x. Right, all these little corners here are x. Now look what's happening. We're trying to find the max volume, right? So the thing I'm trying to maximize with optimization is the volume. So remember the way to find volume? It's length times width times height. So let's talk about how to find these sides here. Now, if we're folding this thing up, I'll tell you right now, this is going to be x. Right? That's the little panel you're folding up. So that's the height. Height's this x. Let's look at this side. This corner right here. Right? So all of this is 40, but you're cutting off 2 x's, right? An x on each side. So this length right here is only going to be 40 minus 2x, right? Because the whole side is 40, but then you cut off these little x sides. So 40 minus 2x. And likewise, right here, that would be 25, but then you cut off these 2 little x's again. So it's going to be 25 minus 2x. So we get this. Right? How do we find volume? Well, remember length times width times height. So it's going to be x times 40 minus 2x times 25 minus 2x. So that's my optimization question. Like, that's the way you set up. There's a volume. What do I do now? Well, I'm trying to find the max volume. So you know what that means? So notice it's only one variable. I'm good. I don't need a constraint. I use what I have. So what does that mean we do next? Well, you multiply it out, take the derivative, set it equal to 0. Right? Good old distribute. 40x minus 2x squared times 25 minus 2x. Now we distribute again, and we're going to get something long. Then we take the derivative, set equal to 0. And then, let me get the actual answer for this, because I'm probably going to care. Okay, so again, skipping on the math so I don't waste a bunch of your time. This would be, so if you multiply this all out, you would get 100,000x minus 130x squared plus 4x cubed. If you set equal to 0, in fact, well, that's multiplying out. If you take a derivative of this, right, just take normal derivative, bring it down, subtract 1 off, simplify it a little bit, you would get 12x squared minus 260 plus 1,000, right? Nice, pretty numbers. You can actually divide factor all that by 4 and stuff, but anyway, you're going to get this if you factor it correctly. Right, and I split it. Remember, that's nothing. 4 equals 0, it does not. So you don't get a critical point. Stop doing that. Stop messing around. This set equal to 0. Add 50 divided by 3, so x is going to be 50 over 3. X equals 5, right? So this is why I want to show you this one. Because now look at, you have 2 critical points, right? It's 50 over 3 and 5. I'm not sure which one's the min or max. What are we trying to find? The max, right? I'm not sure. So how do you go figure out which one's the max? Well, if they're both maxes, that's not going to happen. But if they are, though, you plug them both back in and see which one gives you the max volume. Right, but how do you figure it out? Well, you can do a sign chart if you want. Easiest way is probably the second derivative. So this was my first derivative. The second derivative would simply be 24x minus 260. And what I do is plug both of them in. You plug in 5, you get 24 times 5 equals negative 140. If you plug them both in, I'll tell you right now, 5 is the winner. Right, but that's the idea. You plug this in, you would get a positive, which is a min. You plug this in, you get a negative, which is a max. So double prime 5 equals some positive number. So this is my max value. Right, now look at the question in this one. What's the square size must be cut out? So I don't have to actually find the max volume. I am done. The square size is 5. Right, and that's the way it works. Same concept as before, right? You have to optimize this. Well, how do we optimize it? We try to optimize volume, so let's find what the volume is. The hard thing was that the x squares were x's, so we had to figure out, okay, this whole length is only 40 minus 2x, you're taking out the 2x, the x squares. This whole length is 25 minus 2x, and that's x. Right, and then volume is this length times width times height. Multiply it all out. It's like numbers I know. You get this, set the derivative, right? But once you do that, it's the same concept. Take the derivative, set equal to 0. How to factor it? Well, I use the answers in the book, but whatever. Right? You get your point, get your values. Now in this case, we've had 2 of them. So how do you tell which one's the max? This is where you do the sign chart or second derivative test, right? This is where it really comes to help you. So either way you do it, 5 is the max. Now keep in mind, if I had a calculator, then let me use the calculator right here, I would have just graphed it. I would have just gone, right there would have been like, said you could, well, I would have just graphed it, and I got maybe you get something like that, and then use your calculator to find the max. And that would be your answer. Right, so if you get these calculators, plug it in, graph it. Done. Okay, let's go to the next one. The total cost of producing X blankets per day is this amount, dollars. For this production level, each blanket must be sold for 23 minus $1.5 X dollars. How many blankets should be produced to maximize the total profit? Right, so it's like an econ problem, right? Econ and math working together again. Right, so total profit, first part of this, right? Total profit is always, it's like revenue minus cost, right? Money you make versus money you lose. So look at this problem, right? My cost is this. Now here's a little tricky part. My revenue is this per shirt, right? They didn't say this was how much you made per shirt. They're just saying, hey, you make this, each blanket, sorry, per blanket. So this is how much you make per blanket, right? So it's not, your revenue is not going to be that. It's that times the number of blankets you sell. So it's this 20 times 1/2 x, right? Because times each blanket you sell. So that many dollars times each blanket you sell, minus the cost, which is this per blanket. So it's already like baked in the x. So I don't need to multiply this one by x. It's already kind of listed right there. It says it's per blanket. So I get this. Right, so that's the setup, right? My profit is, I make this many dollars per blanket, so times by the number of blankets I'm going to sell. Then subtract off the total cost per blanket, which is, again, that's already like mixed in, so that's that. All right, and that's my equation. There's only one variable, so what do I do now? Just take the derivative of it, set equal to 0. And then it's like everything else. So if you could do that, you distribute it out, blah, blah, blah. I'm not going to waste your time. You're going to get something that looks kind of like this. Plus 23x minus x squared over 2 minus 8x minus 20. Take the derivative of that, set equal to 0. Blah, blah, blah. It's this math. You get x equals 10. Let's move on to the next one. Oh, and then you got to check if it's actually a max, right? So again, lots of ways to do it. Take it to max, do a sign chart, second derivative test, but that's the gist. Last one. Now, keep in mind this one I put GDC, so you expect to use a calculator. Paper 2. A small population of wasps is observed. That's not the prettiest thing in the world. After T weeks in the population is modeled by this. So this is a population of those wasps, where 0 is less than T is less than 25. Again, another one where it gave you endpoints. And this time they're both in there. So these might be the answers. When is the wasp population growing the fastest? Look at this question. When is the population growing the fastest? So very, very tricky. It's not saying when is the population when is the population the highest? Because honestly, the answer would just be 5,000. That's like the upper bound. But how do you do it? You just graph it. Right? If you're trying to find out when that's the highest. That's not what this is asking. When the population is growing the fastest. Growing the fastest is the rate of change, which we learned earlier, is a derivative. So we're trying to find the max derivative. Right? So we're not trying to find the max of this, which is 50,000. We're trying to find the max of the derivative. Right? So how are we going to do this one? And again, you got to use a calculator because this is going to be crazy without a calculator. First, we got to find a derivative. Right? So, take the derivative. Now look at this problem here. So, I think the easiest way to do it is quotient rule. You're dividing, obviously. You could move it up if you want, but that just gets messy. Let's do quotient rule real quick. So, let's find the derivative. Do a little quotient rule. So, this is u, this is v. Right? Quotient rule is u prime v minus v prime u. Derivative top over the bottom. It's in your formula sheet. Doesn't matter. Over the bottom squared. Right? So, let's go u is 50,000. Which would have been the max of the original, by the way, not 5,000. U prime is 0, right? Constant, nice, easy. V is 1 plus a 10,000 e to negative 0.5 t. That looks scary, but remember the derivative is, well, that just goes away. Derivative e, copy it, and times by derivative of the power right there, which is be negative 0.5 or negative 1/2. So it's be negative 500 e to negative 0.5 t, right? So 0.5 is 10 to the 1/2, that's why I did that. So that's the derivative of v prime. So if you use the formula, u prime, so it's going to be 0 times that top, but it doesn't matter because 0 wins, 0 always wins, minus the derivative of the bottom, which is negative 500 e to negative 0.5 t times the top, 5,000, 50,000, 5,000, all over the bottom squared. And this is where it's like disgusting. Right, like that. If I simplify that, I'm going to get positive 50,000 times 500 e to negative 0.5 t all over 1 plus 1,000 e to negative 0.5 t squared. That should be squared. So that's my derivative. Right? So now again, we're trying to maximize this. This is what we want the max of. Want max. How do you find the max? Take the derivative. Second derivative, set equal to 0. I don't want to do that. You don't want to do that, right? That's going to be disgusting. But don't forget, we can use a calculator. So the way you want to find the max of this is just graph it. Graph the derivative. Graph that thing. Right? Graph it. Make sure your window goes from 0 to 25. Because you want to find the max. Again, it might be 25, might be 0. Graph it. Make sure you fix your window. I would try to do this in class, but my TI SmartView trial period is over, so I can't bring up the calculator. But I'll tell you right now, the graphs look something to this effect. And the answer to the max would be at about 13.8 weeks. Right, this is where you'd go graph it second, calculate, or trace. Then you look for max. Then you go a little bit left and a little bit right, and then it'll get you the answer, 13.8 weeks. So that's the idea.